you have written a program. So when I say program, you should think it is an application, or you can think it is a kernel, or whatever it is. It is a program, means a piece of code, that's it. Okay, it's not specific to any application or any kernel kind of thing. Sorry, it can be a device driver as well. So when you have a piece of code, that can be any language, I should say. So the first thing what you see is misbehavior of your program. That means, so the program is not doing what you are what it has to do basically. Let me give you an example, right? Let's say I have if you take the networking, right, I have received 20 packets from the other partner, but in my stats, right, when I use any eth tool command or some other program to show you the stats of that particular driver, especially if you take the network driver, that shows you that there are only 10 packets in the, it has received only 10 packets, though it has received the 20 packets. It shows you that it has received only 10 packets. That means somewhere the count has gone wrong. So somewhere you are not updating the receiving packets statistics properly. Clear? So one more problem could be, right, let's say you have deleted an element from a let's say a linked list. So but after that, once you have deleted, once you next when you print that linked list, you are seeing that more than one element has been deleted. That means this may be because the pointer manipulation has gone wrong somewhere. And one more problem, one more example here may be that, let's say you have added, again this is in the network device drivers, you have added let's say 10 multicast addresses to the device driver, but it says that there are only 5 and some of the addresses are wrong. Even though you did not add some of the addresses to this multicast addresses to this driver, it says that more than 10 addresses are there. So these kind of problems are there, and sometimes, right, some of the code path is not being executed, though it has to be executed. Some of the condition is not hitting, though it has to be hit. So these kind of misbehavior of the program you may have actually. So this is one of the widely problems that you see in your programs. So you need to find out where the problem is there. This kind of problems, misbehavior problems. So this is most of the defects as of now I have fixed, right? They are from this particular misbehavior, not exactly that the program has crashed or kind of things. The problem is here is misbehavior, most of the defects. So the next category is the memory leaks. So yeah, you know that memory leaks, right? So you have allocated some memory using any dynamic memory allocated functions like malloc, whatever the functions that you have, your own functions. You have allocated some piece of memory in the heap section or somewhere, but you are not freeing it, that memory, whatever the memory that you have allocated. So what I say, this may be one of the reasons for the misbehavior of your program. Let's say, for example, as I told you, the example I told you is you have received 20 packets, and these all 20 packets might have been queued somewhere. Hello, who is this?
Hey, Mohan, sir, just Niana.
Oh, okay. Can you please mute your audio?
Sure, I will mute it.
Yeah, sure. Okay, thank you. So the second problem what I see is the memory leaks, as I told you, right? This may be side effects of the misbehavior, the thing that I was explaining you, right? You have received 20 packets and you have stored these all 20 packets in a queue after allocating some memory, but your count says that there are only 10 packets. So after you have done with these packets, you are trying to free this memory, so your count has only 10, then you are trying to free only 10 packets, not the 20 packets. That means the memory that has been allocated for the 20 packets. So then you are losing the memory that has been allocated for the more 10 packets. So memory leaks. And let's say you have allocated some pointers, and you have passed these pointers to some other functions where you are not freeing it properly, though you have to do it. So these kind of things lead to the memory leaks. So this is the second kind of problems when you in a program maker actually. So other thing is the invalid memory access. This is also widely things. So when you have the invalid memory access, most of the times your system will crash, or it may give you the segmentation fault kind of things, depending on your program. Basically, if it is a kernel, right, it may give you the oops kind of thing. If you have the application, it may give a segmentation fault, it may have some other problems as well. So right, this illegal memory access means, let's say if you take an application that you have an address space where you have the access to that a piece of memory, but in your program you are trying to access a memory that is not yours. That may be one of the reasons. Another reason is, let's say you have a read-only memory. Basically, that means a page that has given to you has been made as a read-only, but you are trying to write into that particular memory. So in such case also you are trying to access, or you are trying to write into an illegal memory kind of thing. So in such case also you may get something called segmentation fault. And one more thing is, let's say you have allocated some memory and you have freed it using any of the free functions, but you are trying to access the memory once again. So this may be the another violation kind of thing. And one more thing is, let's say you are an application. So as an application you should not touch the kernel memory, but somehow you are trying to access the kernel memory directly without going to the interfaces that are provided by the kernel. So this leads to the invalid memory access. So the other one is the invalid instructions as well. Though when you write a program, most of the times you will not see this thing, but when you write a program, you will compile it with one of the compilers, and you are trying to execute this particular executable for program in another processor, or a processor that doesn't support some of the instructions. In such case you will see the invalid instruction problems. So the fifth one I see is the synchronization issues. So when you have a different kind of threads, or when you have the different kind of contexts, so you need to you need to synchronize some of the global data between these threads or between these contexts. For example, if you take the application, there may be multi-threaded applications. In such case, let's say a data is being shared among these threads, right? So you need to synchronize this data between these threads. And when I say context with respect to the kernel, right, there may be different contexts. Let's say a process context or interrupt context, and if you take Linux, right, there is something called soft hierarchy context. So in these any of these contexts, some of the data may be shared. So you need to take care of this data is not being accessed by these all contexts simultaneously. So if that happens, so you are actually your program will not give you the correct results. So this is also why very difficult problems in your program that cannot be easily debugged. So as you know, there are a lot of different techniques to synchronize the data. So these are the five broad categories where I see the a program may suffer from these things. So once you have this problem, once you find that you have one of these problems in your program, so you have to have a technique where you can go and see where this particular problem is there. Let's say one example I will tell you. You have this memory access violation, as I told you, right? Let's say you have got a segmentation fault. So then your next thing is you have to go and find out where this particular segmentation fault is occurring, at which instruction this is happening. That is the first thing you are going to do. Next thing is why this particular segmentation fault is happening. So what problem that you are doing, what kind of memory you are trying to access it, then you have got this segmentation fault kind of things. So any of this thing, you take any of these categories of these problems, right, you need, what I say is, you need some tools. Basically you need some techniques. Even though I don't say it is a tool, you need some technique to find out where this problem are there in this in your program. That's what I say. So what I say is, as I told you, right, so debugging is not actually trying to fix a problem. It is actually trying to find out where the problem is. So you need the debugging techniques to find out the problem, not to fix the problem. So what ultimately is there, once you have found the problem, you have to use your coding skills, and you have to use your mind, and as a developer mind, you have to fix that problem. So for this thing you need to go through the whole code, and you may need to change the whole design, or it may be a simple fix as well. But a debugging technique, a debugging tool will not tell you how to fix a problem. This is to debugging tools or debugging techniques are just to find where the problem is. Clear this thing. So what I say is, before you search for a tool, basically, actually what I say, before you search for a tool which can debug a program, once you have got this problem, so what I say is, you have to learn what you want to debug, actually what you want to find out in your program. So what the problem is there, actually what problem you are seeing, so what kind of information I need, so that I can be able to find out where the problem is. So in that case, based on these things, you analyze this thing. I want this thing, for example, I want to know the exact line of the code where this problem is happening. One more thing is, I want to have the local variables data at that particular time when the segmentation fault has happened, or I want to have the global data when that segmentation fault has happened, and I want to have the all other data structures, I want to access it, and I want to have the backtrace where this particular from where this particular function has been called. So you just write down what you need first of all. So once you have written down these things, then you search for the tools, if there are any debugging tools, to get these all kind of information. So these before you search for, as I told you, before you search for the tools, what I say is, you have to find out what you want first of all. So this is called the debugging technique. Basically, it's not a finding a tool. Actually, you need to learn the debugging techniques instead of the debugging tools. That's what I say. So what we do in this particular session, right, as I told you, so we'll take some examples here. I'll go ahead with the memory accessing problems in this particular program. So I'll take one example. I will show you there will be a problem in a program. So I'll show you what information I need to find out to get the problem of this particular program. So then I will introduce you some of the debugging tools that are there to what I say, to ease your work to find out the problems. So any doubts as of now? So what clearly I'm saying this, a debugging technique or debugging tool is not to fix a problem, as I told you. It is to find out where the problem is. This thing, sometimes it is not even it is not even simple to find out where the problem is. Even if you have the debugging tools as well, you cannot find some of them. So you may get some clue that in this particular piece of area you may have the problem. So then you, as a developer, you have to go and read the whole code, and you have to find out where the exact problem is. So debugging tool is just to narrow down your search. It is not exactly to find out it is not exactly to pinpoint where the problem is. So any doubts as of now? So let me take one example here. Okay, so I will show you one two different kinds of examples here. One is a single threaded application, another one is the multi-threaded applications. So I'll take one single threaded application where I have a problem like memory violation access. So I'll tell you how to debug this program when you have the correct tools, I mean kind of debugging tools, and I will tell you how to debug the program if you don't have these tools as well. Okay, let me start with the program here. So here you can see I have a program here, sftp.c. So this is a small program. Basically I have written it is it has a FTP client actually. So what it does now, it will take 3 command line arguments and it will try to connect to one of the FTP servers. Then it will try to provide you a prompt where user can type some commands to get a file, to receive a file, or to send a file kind of things. But this is very small program. I did not write complete program. I have written very just small program to show you the segmentation fault example. So I think you can see this program here. Let me start with main function here. So this is the program. As I told you, right, I am taking 3 arguments. As you can see, this is the my uses of this program. I will take the host name, I will take the username, I will take the password. So what it does now, once it takes these 3 information, it will try to connect to this particular host. So once it is connected to the host, it will try to provide you a prompt here, so where you can type your commands to do the FTP things like receiving the file or sending the file kind of things. So once I got this thing main function, right, so you can, once I do the basic sanity check, I'll go here, I'll call one function called connect. Here you can see I am passing 3 arguments, argument 1, argument 2 and argument 3. So as you know, argument 1 will be this particular host, and argument 2 will be the username, whatever the username that the user has entered, and argument 3 will be the password that has been given by the user. So I'm passing these 3 information to a function called connect. So our task of this connect is it has to put a request to the FTP server that is given in this particular host, and it has to establish a connection with that thing. So give it the given username and the password. So once I go to this connect function, you can see this, I have written this connect on top of it, but I did not do anything else here. Look at this function. I have taken 3 parameters as the connection, the host name and the username and the password of it. Once I take it, is first thing I'm doing here is basically I am taking a local copy of these all 3 information that has been given by the user. So this information, I think I would like to use this information after if there is any reconnection kind of things. So that what I do, right, so I'm allocating some piece of memory for each of these things. So I use a function string length here. I would like to find out all this length of this strings given by the user, and I'm allocating memory using the function called malloc. Okay, so as you know, the malloc returns one white pointer. I'm storing it to a user pointer. So here I use a function called my string copy. I have written my own function here. So I'm copying this host name and username and password into my local variables. They are not actually local variables, they are global variables here. You can see here I have declared as a character pointer. But what is, instead of I use this malloc function, I have used my own function called xmalloc. So here it is, you can see the xmalloc definition here. It just returns you the null. That's it. So my intention of this program here is, you can see this thing, once I allocate the memory, I am not checking the return value of this function. So as you know, malloc will return you the address of a memory that has been allocated if it can allocate successfully. If it cannot allocate the memory successfully, it should return you the null. So what my point here is, all the return values must be checked by the user, with the programmer. So before you're trying to use that particular memory. But you might forget these all kind of things, the return values. So you will run your program as many times you run your program in your development stage, you will not see this problem. This because your malloc may not fail most of the times, right? So once you ship this product to your customer, there may be a scarcity of the memory, so your malloc may fail. In such case, the malloc will return you the null pointer. So thus at such case you will see this particular problem. So if you know that this problem occurs at your development stage itself, you should have fixed it definitely. So you could have used a debugger like GDB. You could have find it easily, but it is not an easy problem. So it will not it cannot be reproduced easily. So you need to have a system with a scarcity of memory, and then only you can see this problem. So what I'm trying to simulate here is, I have written my own function. I'm trying to return with the null pointer here. So as you can see here, so this user should contain the null pointer, but I am trying to use the function my string comparison copy. I am trying to copy this host information into the newly allocated memory. The host here, host or user or password, any of these things should be null pointer. Clear? So clearly there is a problem here. So what I will do, right, I'll try to compile this program first of all, then I will get a segmentation valve once I run this program, as you know. So then I will tell you what information I require to find out these kind of problems. I mean, I should be able to find out there is a problem at this my string comparison function. I should be able to find out what problem is there actually. What address you are trying to access, why it is giving you the segmentation fault kind of things. Okay, if you see here, we have the global variables, 3 global variables here, and you have the some parameters to my string comparison, string copy, and there is a local variable save, and what else? To the connect function there are 3 arguments. Okay, so any doubts here? Now let me compile this program. So I use gcc command, right? As you know, I'm working on Linux, so I have the Ubuntu desktop here. So I have installed gcc command. So though I have here I have a 60-bit 64-bit compiler, so 64-bit compiler architecture, but I will try to explain you this on the 32-bit first of all, then I will explain you on the 64-bit. So I have a gcc compiler, and to compile a program with 32-bit I have a flag here -m32. So the followed by the sftp.c-o sftp. So what it does, right, it will this program sftp.c will be converted into executable file as a 32-bit program executable file. Any doubts here? So I compiled here, so I have got this executable file, you can see it here, ftp file. We have a command sftp, you can see it says that my program is a ELF 32-bit executable file, so it is built for the Intel architecture, x86 architecture. So once I have this program, let me run this program now. So /sftp, once I try it, it says that I have to pass 3 parameters, command line arguments, host name, username, and the password. So let me pass something here. So let's say host name is kenare.org, kenare is username, let's say some password I gave here. So once I give it here, so I am waiting for one thing here. Once I press here, you can see something called segmentation fault here. So you know what the problem is now, but let's see. Once I have run this program, I have seen the segmentation fault. Got it? So now our intention is to find out what the segmentation fault is, at which line you have the segmentation fault, and why the segmentation fault is, and what you are trying to access, why you have got the segmentation fault. This thing. So for this thing, what I say is you need at least these kind of information. Well, let me hop it. Put a color as blue. So the thing is, first of all, I need to find out the instruction address. Where the problem is. So once you have the instruction address, next thing is what are the local variables? What local variables contain? At least to find out it. and what were the parameters to that function. What were the parameters to that function? Who has called this function? So what were the values of, or what was the data, what was the globe, what were the globe, what would I say, what were the data of global variables. So yeah, what else I require? So I know the instruction address, so it will tell you where the problem is, and I know the local variables, so that we can see if there is any problem with the local variables, and I know the parameters of the function, so that I can know where the problem is, if there is a problem with the parameters. And one more thing is, I will know who has called this particular problem, where the problem is, and another thing is what were the data of the global variables. So I think this is enough to find out. One more thing is, we need the information of the registers, I mean contents of the register at the time of the class. So yeah, so this information, once you have, if you have these all information, I think we should be able to find out what the problem is, where the problem is. Clear this thing? So what I say is, instruction address, first of all we need to find out the instruction address where the problem is. What we require is the registers information. At least if you take the x86 machine, you need to find out the instruction pointer, what the instruction pointer register has currently. So when the segmentation fault happened, so what thing you have want is instruction pointer. Instruction pointer. This contains the address of the fault instruction. Yeah. So next thing what we need is the local variables. To get the local variables, what we require is the stack data. We need the whole stack data. So as you know, when you call a function, basically all the arguments to the functions will be copied onto the stack. Then the called function will access those arguments using the stack. So one of the ways to pass arguments to the function is using the stack. Another way is using the registers as well. So as I told you, we are also getting the information of the registers. So it contains both registers as well as the stack contains the local variable information. So what is the next information is the global data variables. As you know, global data will be there in the data segment. So we require the data segment at that particular time of this particular process. When you have the process, you know that there is a data segment, there is a stack segment, and there is a code segment, and there is something called heap segment as well. So if you know the data segment, you will be able to find out the what variables, global variables contained at that particular time of the crash. And if you know the stack thing, you will be able to find out the what were the local variables and what were the arguments containing at that particular time of the crash. And if you know the instruction pointer, it is a register in the CPU, then you will be able to find out the at which instruction the crash has happened. So another information we require is the called, who has called this function. So we need to find out so where this particular call has come from, this particular fault instruction. Let's say main, in our case, main has called the connect function has called the mystring comparison function. So this way there is a call trace. So if there is a problem in the mystring comparison, you should be able to find out who has called mystring comparison. This is because your mystring comparison may be called from different code paths. So you should not assume that this function has been called by particular this function. So you need a call trace to the down to the your program, so that you will be able to find out where you have come from, so that you can go to the previous function, you can see if there is any problem in that previous function, and you can go to that previous function, you can see if there is any problem. So this way you need the call trace. So for this thing you need to take the help of the architecture most of the times. So in my case at least, I'm using this x86. This all information, this call trace information will be there on the stack itself. So for this thing, to get the call information, I again require the stack. So next thing what I require is the, if you have any if you have allocated some memory, global memory using the dynamic memory allocators, so this thing will be there in a segment, not exactly a segment kind of thing, something called heap kind of thing. So if you know these all information, what are the instruction pointer along with all other registers, I'll show you why we require the all other registers, and we require the stacker. So where you can see the local variables, or where you can see the arguments to a function. This is very important. Data at that particular time, basically when the program has crashed. Next thing what we require is the data segment. Once if you know the data segment at that particular time, so you will be able to access the all global variables. That means what were the global variables contained at that particular time of the crash. So next thing, once again, if you want to have the call trace of this particular back trace, we say something stack trace, you require the again stack, at least if you take the x86. So another thing is the heap. This is required if you allocate the memory using any dynamic memory allocators, and if you want to see what information is there in that particular allocated dynamically allocated memory. For example, you have allocated a structure using this particular malloc function. So you want to see what were the contents of that particular structure at the time of the crash. So for that thing you require the heap segment as well. So totally I require, once if I know this at least these 4 information, instructions and register, stack, data segment and the heap segment, I should be able to find out at least, so I should be able to narrow down where the problem is. Clear this thing? So for this thing, at least once as I told you, this problem will not occur frequently, so it may happen anytime, we don't know. So you can't use ZDB, and you can't do step by step if you to find out there is what were the contents of that thing. So at the customer place this problem may occur. In that case, so once the this problem occurs at the customer place, he will send you a mail saying that, man, it has crashed, my program has crashed, right? My program has generated a segmentation fault. In that case, you need to ask your customer something called core file. Got it? Basically you require these all information, right? As I told you, you require these all information. So these all information will be there in a file called core file. So with the help of the operating system, you can tell the operating system that, man, if there is any problem with my program, if it has crashed, or if it is there is some problem, severe problem, then what you must do is you have to take the footprint of my process, I should say whole address space of my process, and store it into a file, so that I will take that file, I will analyze what happened to my program. Clear this thing? So when I say a core file, basically when I say core file, it should contain these all information. What is this? The registers information, stack information, data, and the heap segment. And along with this thing, it has to tell you the which signal has basically generated this particular core file, and what were the program that generated this core file, and what were the PID of that program, this kind of extra information, and what were the signals at that time when you see this problem. So these all information should be stored in a file called core file. So if I take one example here, let me, so I have a command here, core dump. So what core dump? So this is the information as I told you previously. So when you take a core file, it should contain this information. First information is the process data, process status basically. So which signal has generated this particular core file. So what were the pending signals at that particular time when it has crashed? This may be useful for your case. And one more thing is, what were the blocked signals at that time? Block means some of the signals you may block using the sigproc or some blocking functions, right? So that information also will be given by that. And one more thing is the process ID of the process, and the PID, parent PID of that also will be given. And one more is set of registers. So this contains the all data of that particular registers. Let's say if you take, in case of x86, there is a register called SP, stack pointer, ESP. So that contains the current stack pointer. This way all information will be there in this particular process status. The first thing, a core dump core file contains this process status. So the next thing is the process information. They contain some more extra information of this process, like state of the current process. That means while the process was running or not, it was sleeping, these kind of things. And the other thing is the important thing is the process name. What was the process name? Let's say in my case it is a SFTP, right? So that name will be given. And one more thing is, what were the arguments that have been passed to this particular program? Arguments means command line arguments. So this information will be there in a section, you can say, kind of thing, process information section. So these two information, process status and as well as the process information. And the next thing you have is the thread specific information. Let's say if your application is a multi-threaded application, so you need to have the information of the other thread as well. Let's say if you have 4 threads in your program, so you should get the current threads information as well as the other 3 threads information. So then only you will be able to see where the problem is there. While a segmentation fault happened, what was the other thread doing? Where was the other thread? These kind of all information you can get. So there is something called thread specific information. So the next thing you have is the what were the files if they were memory mapped, right? Let's say in your program you have used some system called like mmap, and you have mapped some of the files. You want to find out what were the files that were mapped before that particular segmentation fault happened. So these all information will be there in this particular. What was the name of that file that has been mapped, and what is the start address where it has mapped? These all kind of information will be there. And the 5th information, as I told you, is the process address space. This is very important for us. Data segment and the stack segment and the heap. Code segment is actually, the section is there, but whole code segment information will not be there, because when you have the executable file, you have the code. So right, you need not to have this all code inside your core file. So what I say here, you have these 3 information: stacks, data segment, stack segment, and the heap segment. So that's it. So let me show you the briefly what information a core file contains: process status and the process information, like, and arguments, and the thread specific information if there are any threads in that particular process. One more thing is memory mapped files information, and the final thing and very important thing in our case at least is the process address space. Whole process address space will be copied into the core file. So let me tell you who generates this core file and when this will be generated. So let's, as I told in our case, when I try to access that null pointer, so what happens is, right, the CPU will try to get the physical address for this particular 0. As we know, this we use all virtual or logical addresses. So the CPU will try to convert this into physical address. So but there will not be any map for this 0th address. The kernel will not map any physical address for this particular 0. So in such case, the process will generate something called page fault exception. So then the one of the functions of the kernel called page fault function will be called. In that function, the kernel will try to see whether this particular address is valid or not. So if that particular address is valid, and that address is, you have the right to access, the process has right to access it, so it will try to, even though the address was not mapped to the physical address, now the kernel will try to map it immediately, on demand mapping kind of thing. But if the kernel sees that the address is a problem address, that means in our case it is a 0 address, that will never be mapped to the physical address. In such case, it says that it is a bad address, bad area, so it will now generate a signal to the process. Clear? In our case, it is a segmentation fault signal to the process. So once it generates the signal to the segmentation process, it will try to create a file called core file. So in this core file, it will try to embed these all information, whatever the information that I have shown here, right? It will try to embed these all information. So it will create this file in your current directory where your program is being run. So as you know, right, when you have started a process, the process has some information like address space, namespace, I should say, right? What was the current working directory of that particular process? What was the file system, that main root file system of that process? This kind of information. So in the current working directory of that particular process, this a file called core file will be generated. So that core file contains this all information. So once we have to now ask the customer to get to give us that core file, so that we can analyze what happened in our program. So this core file basically, right, will be most of the times will be specific to the operating system, not exactly to the architecture, I should say. Both I should say it is a platform dependent most of the times. Platform means, as you know, right, it is a operating system plus architecture. So in Linux, at least, these core files are ELF files. ELF, as you know, right, you have the executable file, you have the object file, .o file, executable file, and shared objects. These are all files basically based on a format called ELF, executable and linkable format. So this there is another object file along with these three things. What are they? Object file, relocatable object file, executable object file, and the shared object file. There is another object file called core object file. Clear? So this core object file, if you take any ELF specification, you can go to the internet, Google, and you can get this ELF specification. So there they will explain how this particular core file should be generated, what should be the format of it. But Linux has its own format, basically how it is generated, but ELF, it uses the ELF format. So in the ELF format, if you once this file is generated, core file is generated, you need to have a tool who can understand this ELF format, so that you will be able to decode these all the information, like this process, all address space and registers and the stack, everything you can decode. So now our responsibility is, before you run your program at the customer place, wherever you want to, so you have to tell the kernel that, man, I want to generate a core file whenever there is a problem. By default it is enabled, but this is your process should have something called resources. There are something called resources of a process. Yeah, hello. So your process has some resources, like how many new processes it can create, how many files it can open. These kind of resources are there. I mean, resource limits, we say. A kernel maintains a list of resources for each process. So to generate this core file also, you have to tell the kernel that, man, you can generate this much core file. Let's say the core file is 2 GB, 3 GB. It cannot generate automatically. You have to tell this kernel that you generate this much size of the core file, because you will have your own limits in your disk space kind of thing. Then you have to tell the kernel that I want you to generate this much core file, not more than that. So when you say that information, then the kernel will go and generate a core file whenever there is a problem with your program. So, but this core file will not be generated for all kind of problems, as I told you, right? So there is, as I told you, when there is a problem in your program, basically the kernel will try to send a signal to the process. So there are, as you know, there are a lot of signals, at least 32 signals, normal signals. So for some of these signals your core file will be generated, not all of them. So what I would recommend you is go to the man 7 signals. I think there you can see some of the signals, like let me show you that man signal. It is a man 7 signal. So it gives you the overview of the signals. Here you can see some of the signals for which a core dump will be generated. Here you can see this. These are the signals. There is something called action here. Core is there, right? Wherever you see this thing, for those signals only your core file will be generated. So one of those things is the segmentation fault. So in our case it is a segmentation fault, so that we will get the core dump. So what, as I told you, right, as a programmer, first of all you have to tell the kernel that so you can generate this much core file. So the size of the core file should be this much, not more than this, the kind of thing. So if you don't tell that, by default it is 0. So that means when there is a problem, then there is a segmentation fault, it will not generate you the core dump. Now you have to use some of the functions given by the kernel, I mean they are system calls, to set this limit of the core file size. So I think there is a function called set r limiter. Yes, there is a function called set r limit. You can see this thing, set r limit is there. So use this function, you set how much size, how much should be your size of the core file. So then if you set this thing, then the kernel will be able to generate the core file. So but if you don't have, basically you have to use this command, this function, but in my case bash is my the shell script I am using. So bash will provide you one function called ulimit. So using this thing you can set the limit of the some of the resources. So as you know, this core dump, right, for this core dump you can set limit using one flag using the -c. That means I am telling you limit that man -c. That means for the core dump you set this much, let's say 1000 bytes kind of thing. So basically what people do now, they will say unlimited. That means you generate as much file as you can. That means you take, let's say my address space is 100 MB, you just take whole 100 MB and just put it into the core file. So once you say this thing, then only you will be able to that the kernel will be able to generate the core file. Otherwise you will not see a core file. So another cases where this core file may not be generated is, so you don't have, hello, so the process that is executing doesn't have right to what is it right to actually access that particular directory where this core file being generated. In such case also it may not be generated. That means you need to have some privileges. That means you need to have a writable directory where this core file can be generated. But most of the times, as you know, right, once you are running a program, that directory will have most of the times the yes. So now you can see this, I have used ulimit function and I have set my size of this core file to the unlimited, whatever I want it here. So once you set it, you can now run your program to get the core dump. As I told you, it will be generated in the current directory by default, but you can change it. I'll tell you how to change it later. So now let me run the same program once again, SFT program, and see how this core file is generated. Any doubts as of now? So why we need a core dump file, that should be very clear. Our intention is to get the stack information, data segment, and the heap segment, and one more thing is the registers. If you have these all information, we should be able to find out, at least we should be able to tell where the problem may be. So for this thing, so you need these all information. So these all information will be stored in a file called core dump. It's a core file. So this should be generated by the kernel. This should not be generated by any application. There is no other application you have to run to get this core dump file, core file generated. As I told you, all my programs are ELF programs. So you need, there is a binary format called ELF, and you need to enable this core dump feature of this by ELF in your kernel while you build the kernel, right? So there is a kernel option which will tell you you have to enable the code dump of the ELF as well. So the ELF code that is there in the kernel will generate this code dump file. Clear? So once you have that thing, then you can now run the program to get the code dump file. I'm running the program once again here, SFT followed by something. I have to give 3 things, right? The host name, username, and the password. So let me give anything something here. So I gave some random things here. I should be able to see this thing. Core dump has been generated. There is a segmentation fault. So now when I type it here, you should see the file called core generated by the kernel. Clear? So if I type a file on this core, you should see this thing. It says it is a core ELF 32-bit LSB core file. LSB little endian. So generated for the x86. So as I told you, this is one of the format of the ELF. So like a relocatable object, executable object, and the shared object. Core is also one of the file format. So now you have the core file. As I told you, this core file contains all other information, as I told you. Clear? So what information it contains, basically overview of this information. Basically when you take an ELF file, it is basically a collection of sections or collection of segments. If you are aware of this, how this executable program is formatted, or how these relocatable objects are formatted, there are something called sections, then there are something called segments. So basically a relocatable object contains sections, and an executable file contains segments, like data segment, code segment, and the what else is that, stack, this heap segment kind of things. What I say is, so you can this is a core file, is also a ELF file. You can use some programs like bin utils, as you know, right? There is one function, one command called object dump. You can use this command to see what were the segments that are there in this particular core file. So you can use this object file, and there is a flag called -h which says the sections of it, and the core. So object dump -h core, the file name. When you see this thing, it shows you some of the segments. Basically, they are actually segments, but object dump shows them as a sections. So these are the sections you can see. For the first section you see is the node section, and there is a register segment. There are a lot of segments here. So like 17 segments are there. So what these all contains, we'll see later for the time being. So at least once you have this thing, you should be able to understand that this is a core file which contains all information that we want. So to analyze this thing, where the problem is, first let me start with the GDB tool basically. So then I will show you how to see this without the GDB, right? If you don't have any debugger basically. So now use this GDB command. You should have installed this GDB, and GDB command followed by your program, the executable program, followed by the core file. You can see this thing, right? GDB, the executable file, and the core file. You can give this core file later as well, but let's give it here itself, the command line itself. So you give it and type, press enter here. You should see this thing. So once you see here, come here, now it says that the problem is at this particular instruction in the function myStringCopy. Clear? And it says that the problem is the signal that has generated this core file is segmentation fault, that is 11 signal, and the parameters that was sent to this particular function are these things. The program were these things. These all information, whatever this instruction information and this particular command line and the signal information, everything has been fetched from the core file. So now you can see one more thing here. There are no debugging symbols in my particular executable program. So that means there are no debugging symbols, means debugging with GDB is somewhat difficult. So if you know the debug, if you have the debugging symbols, so you will be able to debug it very easily. That because GDB is basically a source level debug kind of thing. To do the source level debugging, you need the debugging symbols. So that we'll see what they are later. For the time being, I don't have any debugging symbols in my program. So now that's why it says that it gives you an instruction address, and the function name, but it doesn't give you the line number where the problem is of your program. This is because you don't have the debugging symbols in your program. That means your executable program doesn't contain any debugging symbols, so that the GDB can go and read these debugging symbols and show you the all information, like where the problem is, the line number of the program, and what were the parameters given to the my-string comparison, my-string copy. Everything will be there when you have the debugging symbols. If you don't have the debugging symbols, it just shows you the instruction address where the problem is. Clear? So the two, it is getting this my string copy function name, because these all names will be, these are like global functions, and these all names will be, there is something called what is that, symbol table. So otherwise other information like local variables information will not be fetched by the GDB. So now once you have got this thing, we know that there is a problem at this particular instruction line instruction. It's actually a binary instruction. It is not exactly a line number of a program. So once you have this, now you need to find out where exactly the problem is, what the problem is, right? So we don't have any debugging symbols. What I would like to do is, right, the first thing what you need to do is, once you have this thing, disassemble. If you don't have any debugging symbols, use the disassemble function and press enter. Now once this, it will show you here there is an arrow mark here. It shows that the problem is here. You can see here the problem is here, and it says that the instruction, you can see here, move instruction, it is trying to take this particular value in this particular register, and it will try to write into a memory where this particular EAX is pointing to. So got this? What I say is, you are doing a move instruction. That means you are trying to write into a memory address where this particular EAX is pointing to. So that is when you have the problem. That means it says that the instruction address is at this particular location. The function name is, as you see, my string comparison, my string copy. Clear this thing? Now we need to find out, once you know this thing, the problem is there in the my string comparison function. Now to analyze more, what we require is what were the parameters that were given to this particular function, the first thing. So then next thing is, what were the local variables of that particular function, what they were containing. These are information we require. Clear? First of all, let's see this thing. We have this thing, right? You are trying to write into EAX. That means not exactly EAX. EAX has one address. So you are trying to write this particular value that is there in the DL into the address where EAX is pointing to. So what you can now at least do is try to print what is the EAX containing, what is the value of EAX, right? So there, as you know, there is a print command, print $EAX. I think should be able to tell what it contains. Print $EAX. These all registers are specific to this architecture. You should know first of all these are things. So EAX now contains the 0. Now it is clear that you are trying to write into a 0th address. That is the problem. And what you are trying to write is, you are not you don't want that information, but you can print it. What you are trying to write is, you are trying to write one number or one character. Basically when you say C, it says that you are trying to write yes into that particular address. Clear? So, or you can use the info registers command. So it will show you what were the registers containing at that particular time of the crash. So you see this all registers information is there. So EAX contains what? 0, and ECX contains A, and ESP contains this thing. So we will see why these all registers information is required later. For the time being, you know that the problem is there is a EAX register. We will analyze more this thing. And one more thing, one more important thing is, as I told you, you have to find out where you have come from. That means which function has called the my string copy. So who has called that function as well. For this thing, as you know, backtrace is a function. You can see the command. It will tell you where you have come from. It says that you have come from main to connect to my string comparison, my string copy. So now your aim is to find out what were the parameters of the my string comparison, my string copy. Clear? For this thing, what I say is, when you see this thing number here, 0, 1, 2, These are things, right? When you have a function, when you call a function, for each function there is a stack frame allocated. Let's say first of all there is a main function. So once your main function is called, a stack frame will be allocated for that particular main function. Got it? So that frame is just like a boundaries. Let's say it is starting from here, it is ending to here. So this stack frame contains all information of this particular main. That means all information means some local variables and return addresses, those all kind of things. So for every function there is a stack frame allocated. So first main is there, so main has one stack frame, then connect is there, connect has one stack frame, then my string comparison is there, my string comparison has one stack frame. So as you know, all these local variables and parameters whatever are there on the stack. So if you know these all stack frames, you will be able to find out the local variables and the arguments to the functions. Clear? So here you have this is the most latest stack frame. This 0th one is the most latest one is the next one, second one is the last one. So here there is a command called frame, info frame. It will show you the frame information of the current stack frame. So in my case the current stack frame is the 0 because that's where I am standing, my string comparison. When you say info frame, it shows you a lot of information. The stack level is at 0th position. That means the stack frame is the 0th position, and it says what is the EAP, instruction pointer at this time, and it is in the my string comparison function. And one more thing, important thing is where are the arguments this particular function. See, this arg list is here now. So it says that arg lists are here, this at this address, and where the local variables addresses are at this particular location. So if you see this thing, there are arguments and that were passed to this particular function, and the local variables as well, where at this particular address. So now our aim is, as you know, right, this is a stack address most of the times. So because these arguments are stored on the stack, now we need to use this address, we need to find out what were the parameters or arguments sent to this particular function. Clear? Yet if these all things, how these parameters will be passed to a function, are most of the specific times architecture specific, sometimes I should say platform specific, and there is something called ABI, application binary interface, that explains you how the parameters has to be passed to the function. In x86 class, what I would say is these parameters will be passed like this. Let's say I am calling, in my case, what is that, BT, right? BT, or where you can use the same command, and there is info stack. Three commands are most of the time they are all alias kind of things. Most of the time they will give the same information. So you use any of these commands. If you see this thing, main has called my connect function. So once main is before main calls connect function, as you know, this connect function has taken 3 arguments. Before main calls my connect function, it will push these 3 arguments. In my case, the 3 arguments are pointers. So these 3 pointers will be pushed onto the stack one by one. So if the last one is if you take my function, right, let me show you that thing. My program name is VAM. Yes. Okay. Core dump. So if you take this program, in my main function I am passing 3 parameters here to that connection function. So the first one is a pointer, second one is a pointer, third one is a pointer. It is a character pointer. I am passing 3 arguments. So they are basically in my, I said it is a 32-bit, right? So you will have the 4 bytes of the pointers. So before this particular connect function is being called, what does this main does? It will take these 3 pointers from starting from here, argument 3. First of all, argument 3 address, whatever it is, the last address, will be stored onto the stack. Next will be the argument 2 address. Next will be the argument 3 address. So these all 3 arguments will be stored one by one. Address of these things, in this case pointers, right, one by one. The first lowermost is the argument v3, that means the last one. Next is the from the right to left, basically all these arguments will be pushed onto the stack. and after this pushing is happen, you have to call a function called connect. So to call this function, there is an instruction called call function, call instruction. So before this call instruction is called, right, basically this call instruction has some other instruction internally. What it does, right, it will take the next instruction address. In this case, for example, if you take, it will take the instruction of the printf, okay, so that will be pushed onto the stack. Not exactly printf, there is a next instruction for this connect. If you take the assembly code, I will show you that thing. So that will be pushed onto the stack. So now first thing is the argument 3, argument 2, argument 1, one by one. Then you have the return address where the function has to come, which instruction has to be executed after the connected function has been executed. So this thing, after this return instruction, what is stored is something called the base pointer. So let me show you one kind of what is it thing here. So thing here, first thing is there is a base pointer, BP will be stored. It is a 4 bytes address, it is a register address. Then you have the return address, then you have the first parameter, then you have the second parameter in our case, then you have the third parameter. So this way, first third parameter, second parameter, first parameter, return address where this function has, where call has to go after this particular connect function, and the BP of this BP base pointer. So let me explain what this base pointer is. As I told you, there is a stack frame for each function. So BP is the starting point of this particular stack frame, and the SP is the ending point of this stack frame. You take any function, so there is a BP, there is a SP. BP should be the starting point, SP should be the ending point of the stack frame, current stack frame basically. So in my case, I have the main function, right? This is the main function. If you think it, main function called the connect function. In such case, main function should have one BP pointer. So that BP will be stored onto the stack before that function being called. So after this thing, now BP will be pointing to the stack frame of the connect function, start of the stack frame of the connect function, and SP will be moved back. As you allocate the memory on the stack, this will be moved down to the stack. So this way, now this BP, whatever I say, this BP is the previous function's base pointer. In my case, after this BP, what should happen is my connect function. After this thing, my connect function's stack frame will be there. So inform all the data of the connect function will be there after this particular BP. So here, whatever the address you see here, right, the info frame, when I say here, this argument list says, it says whatever the address here you have, this thing is the address of this particular BP, where this BP is now. Let's say now BP is in this particular thing. Here it says that BP is. So once you know this address, at that address, if you read data, 4 bytes of data, you will get the previous EBP. So any doubts here? So you will get the previous EBP. Next, what I say is current EBP plus 0. That means I should say this address. I have shown you this, right? Argument list. This address plus 0 should contain the previous EBP, and this current EBP plus 4 should contain the return address of the caller, and the current EBP plus 8 should contain the first parameter, like this. EBP plus 0 should contain previous EBP. Previous EBP means whoever has called me. For example, connect has been called by main, so main's EBP will be there in this particular EBP plus 0. So next thing is the EBP plus 4. It contains the return instruction of the caller. That means once our function is executed, the current function, that means the connect is being executed. After executed, the call has to go to the this return instruction. This is what that thing. So EBP, this is the base pointer as to EBP plus 8. This is always true with respect to the x86. EBP plus 8 should contain the first parameter. So EBP plus 12 should contain the second parameter. So this way, as many parameters as you have most of the times, right, will be stored on the stack, third parameter. Clear? So if you know the if you know this particular if you know this EBP, current EBP, what information we can get is the who has called us currently and what were the parameters that were given to me. This information will be there if you know the EBP address, or that EBP is, will be, I think in this case will be this particular argument list. So as I told you, there is a function, there is a command info registers. Previously I have shown you this thing. It should tell you the what is the EBP now. This is the EBP stack frame start address, current stack frame. It is at this address FFB98898. I think that is equal to that thing, whatever I have shown you, that thing. Info frame, when I say info frame, it shows you the current frame. You can see this thing is equal to this thing. So what I say is, this is the EBP address, current EBP address. Now we know the current EBP address. Now we should be able to find out the return instruction. That means who has called us. And one more thing is, we will be able to find out the what were the arguments that were given to me. Clear? In this first of all, what is there? The EBP plus 4 contains the return instruction where we have come from. That is there, right? So let me print it. First of all, X. So EBP plus 4. EBP is this thing, right? $. So any doubts here? So I am taking the value of EBP, I am adding 4 to it, and I am trying to print what is there. So I want it in a, what is that, slash. So let's say I will print 10 things, and I want in hexadecimal format, I want in word length. So this says that X is a command in ZDB to print the RAM memory, basically, or whatever the address you give, it prints the data from that particular address. So X, I am telling that 10 addresses I want, hexadecimal addresses. I want each number should be of word size. Word size means it can be 4 bytes or it can be 8 bytes, depending on the architecture. In my case, it will be 4 bytes. So if you give this thing, it should print you the EBP plus 4. That means EBP plus 4 should contain what is now 80485EE. So this is what, this is where I have come from. That means who has called me is this thing, this particular instruction. So if you use, I think what is that, info symbol, there is a function you can use this thing. If you give this thing, you can see this thing, it says that this is at the connect plus 176. Now we should be able to tell that my str copy has been called from the connect function. I am telling that if the GDB is not there, you will be able to find out this thing. So it is there at the plus 176. That means you can use the again disassemble function. You can say connect now, right? Connect plus 176. If it says that, it says that you have come from 176, right? 176. This is the thing. So before this instruction, you can see there is a call to my string copy. So whatever we get the call to SE is the next instruction of this function. See, this is the address that we have got, right? So if you know the stack trace, what we are able to now find out is who has called me. So my string comparison has been called, copy has been called by the connect function now. Clear? So next thing what I want to find out is what were the parameters, what were the arguments that were sent by that particular connect function. So we have seen the info frame. One second, let me show you the info frame. Here you have the argument list, same EBP is there. As I told you, EBP plus 8 should contain the first parameter. Clear? So you just again use the X command, plus 8, already it is there, but I am printing it once again. You can see this EBP plus 8 contains 0. That means the first parameter of this function, what is that code? sftp dot c, right? Okay, next vm sftp dot c. If you see this thing, the first parameter is 2. In our case, now we will be able to tell that 2 is 0. That means there is a null pointer, definitely, right? So let's see what is the from now. For that thing, as I told you, from will be there, where from will be at second parameter, right? It is a EBP plus 12. So let's see, let's print it, EBP plus 12. Now you see this from is this thing. So you know that is a pointer to a character, right? You'll be able to print it using the print command. Once you do this thing, and this is a generic pointer, you should be able to convert. So once you print it, right, let's print it as a string now. So it says that the data that is passed to the my string copy is SDF. So I think this is one of the parameters that I gave to my program. Okay, so now we have found what were the parameters, what were the arguments given to my string copy. So using this particular EBP. So if there are more than 1 or 2 arguments or whatever it is, you can use the same procedure. What it is? So EBP plus 8 should contain the first, plus 12 should contain the second, plus 16 should contain the third parameter. So once you got these parameters, so now by this time you know that there is a null pointer given to us, but we need to find out at which instruction the problem is, right? So as I told you, disassemble which function? My string copy, right? So when you do this thing, it shows that the problem is here. Now as I told you, right, there are no debugging symbols here. You are now what you have to do, which line of the code you have the problem is, you need to analyze this particular assembly code. Otherwise there is no other way to find out where exactly is there. But what I should say here, definitely by looking at this thing, you should tell that you are trying to access a null pointer, or you see before this instruction there is another instruction here. You will be able to find out where this EAX is being filled out. Let's see, move EBP plus 8 has been moved to EAX. Now we know that EBP 8 plus 8 has the second parameter, first parameter. So that first parameter, whatever you have, is being copied to EAX. In our case it is a 0. So now the first parameter is being copied to the EAX, and we are trying to write something that is there in the DL into the 0th address. Then we have the problem. Clear? So if you want to find out the line of this means, then you have to go through this all code, like from here assembly code. If you should be able to good at the assembly programming to find out where the problem is. Clear? So that's how you will be able to find out the what instruction has caused this problem. So what address you are trying to access, and then why it has got the segmentation fault. So one more good information you may get here is the info files. If you have this command, right, you will be able to see where these all sections of these programs have been loaded. Sometimes it is very important. Let's say in my case, I am trying to access the 0th address. I will be able to tell that, or I am trying to access the 0th address, so I am getting this problem. But actual case, you have a valid address, but you are getting a problem. That may be because you are trying to write into some read-only memory. In such case, how do you know that is a read-only memory? Right? So that is very important. In such case, what you can do, right? You can use this info files command. So this will tell you where this all file has been loaded. Basically, what all it will tell you what are the segments are there where they have been loaded, and what were the permissions that they have. So when you say info, right, it says you this thing. See this thing, all this my core file has been mapped at these addresses, these all addresses, and one more file is SFT. SFT has been mapped at all these addresses. So what are the other, if there are any shared objects also where they have been mapped in my memory, everything will be shown here. So when you see this thing, text segment or read-only data, right, then you will be able to find out, yes, we are trying to access the read-only memory. So any doubts up to here? So as I told you, right, info frames give you the current frame information, and let's say I want to find, in my case where I say in current frame is the my string comparison, I want to see what were the parameters that were sent to the connect function as well, let's say. All right, so in such case I have to go to the connect function. I have to see what was the frame information at that particular level. All right, so there is a frame command. You can say, for example, currently we are at the 0th frame, right? We can say that I would like to go to the first frame, just frame first. When I say, it says that now you are at the frame connect. Now you can say info frame. Now it will tell you the information of that particular frame. So now you can see again argument list is at this particular location. So when you print that information, there you will see the parameters that have been sent to the connect by the main function. So, and you want to see what were the parameters that are given to the main function, what was the data in the main function. Then again you can use the frame function. You can jump to frame, then you are at the main frame now. So when you say this info frame, you will see the information of that frame. Clear? And another thing, we have got this what is that, parameters list. Another thing is the global variables. The global variables, as you can see, right? So global variables, in our case there are 3 global variables, right? VM sftp.c. When you see this thing, there are 3 global variables. You want to see what was the data that is there at this thing, then what you can do, right? Print user. You can, they are global variables. There will be a symbol table for all of them, so you should be able to see their symbols directly. So now it says that print user contains 0. So if there is some other data as well, it shows you that thing. In my case, password is there, right? You can say print password. This way you can access the global variables, or you can use, I think, info args. You should have the debugging symbol for this thing. So what information you can get from here? We have got the global variables, and we have got the what is it, arguments to the function. All of the functions you can get it like, right? I have told you info frame. You can go to any of the frames, whatever you see in this function, and go to that frame and find out what this address is, and try to print out the all information. As I told you, all parameters will be at the EBB plus 8, EBB plus 12, EBB plus 16, this way. And return instruction also will be there, right? That using which you can find out who has called you. So, and the registers information, if you know this registers information, you will be able to see where is the current stack frame, what was the EBP at that time, I mean base pointer. If you know the base pointer, I think you can find all other information. And if you know the EAP, instruction pointer, that you know that we have all